Hello, everyone, and thank you for watching our short video on extending Intel-x86 consistency and persistency. I'm Azalea Raad, and this is joint work with Maranget and Viktor Vafeiadis. The Intel-x86 architecture provides two kinds of store instructions: plain stores and non-temporal stores. Plain stores are the ones that we're familiar with, where the results of the store are cached to enable faster and more efficient later accesses. By contrast, non-temporal stores completely bypass the cache hierarchy and directly store to memory. This is very useful when avoiding cache pollution, and it's used all over the place. For instance, a quick search on GitHub for the move-nti instruction, which is a non-temporal store, returned over 300,000 results. It's also used all over the place in the C runtime, in large-scale projects such as PMDK, DPDK, and so on. Additionally, the Intel-x86 architecture allows one to declare the cacheability, the memory cacheability of a given page. Memory cacheability can be either non-cacheable or cacheable. The non-cacheable types bypass the cache hierarchy and directly access memory, and include the strong uncacheable type, or UC, and write combining type, or WC. By contrast, the cacheable types go through the cache hierarchy and include the write back type, or WB, and the write through type, or WC. Once again, these are very useful, and they're used all over the place within system level code, including the Linux kernel. Now, as semanticists, we are interested in understanding the semantics and behaviors of these additional features, namely the different memory types and non-temporal stores. In particular, established literature tells us that the Intel-x86 architecture follows the TSO, or total store ordering model. And we wanted to see if this is indeed the case for these additional features as well. To answer this question, let's look at two simple examples. The left example, known as the store buffering example, has two threads, where the left thread writes value 1 to location X and then reads from memory location Y. The right thread writes 1 to location Y and then reads from location X. Now, the question is the annotated outcome allowed? I.e., is it possible for both reads to read the initial value 0 from X and Y and ignore the later writes to X and Y with values 1? On the right here, we have the message passing example, where the left thread first writes 1 to X and then writes 1 to Y, and the right thread reads from Y and then reads from X. Once again, the question is the annotated outcome allowed? In that, is it possible for the right thread to read value 1 for location Y, i.e. observe the second write by the left thread, but read the initial value 0 for location X, i.e. ignore the first write by the left thread? Now, as many of you may know, the TSO model says that the store buffering outcome is allowed, whereas the message passing outcome is not allowed. And remember, we wanted to know if this extends to all memory types or some of them. As it turns out, only the cacheable memory types, i.e. the WB and WT types, follow the TSO model. As for UC and WC, they have different behaviors. In particular, the UC memory type is very strong in that it disallows both store buffering and message passing behaviors. And as it turns out, it is actually subject to the strong sequential consistency model. Finally, the WC model behaves symmetrically to the TSO model with regards to these two examples, in that it disallows store buffering but allows message passing. Okay. Now we understand the behaviors of different memory types in the context of these two examples. And now the question is, what about non-temporal stores? Where do they lie in terms of their behaviors? Well, if you're to trust the text of the Intel manual, it says that non-temporal store instructions treat the memory being accessed as WC type. That is to say that according to the Intel manual, non-temporal stores have the same semantics as WC memory. So we wanted to put this hypothesis into test and see if this is indeed the case. It turned out that actually the Intel manual is quite inaccurate, in that when we replace the plain stores in these examples with non-temporal stores, we observe both the store buffering behavior and message passing behavior. So if we had non-temporal stores in these examples, both of these behaviors would be allowed. In other words, the WC memory types and non-temporal stores have different semantics, unlike what the Intel manual says. And this is why it was absolutely crucial for us to validate the semantics of these extended features. So to sum up, we have formalized an extensive Intel-x86 consistency model that includes memory types and non-temporal stores. We have developed our semantics both operationally and declaratively and prove them equivalent. And in fact, we have empirically validated our model via extensive testing. We have also built formal models for the persistency semantics of these additional Intel-x86 features, but we didn't have time to go through that in this short talk. So if you're interested, please come along to our full live talk on Wednesday, January 19th at 18:55 GMT. Thank you very much for listening. See you all on Wednesday.